Hi guys, so our third lecture in our learning unit here on complex ionic equilibria is probably as rough as it's going to get, I promise you that. This has to do with titrations of weak acids with strong bases. And as kind of the companion to this, as an in-class problem, I'm going to have us work on weak bases with strong acids. Now, again, we will not do a weak-weak combination. That gets to be fairly complex. So that's not something we're going to talk about here in general chemistry. So we've again had strong acid, strong base, which we did in our last lecture. And so we're going to sort of merge things from our first lecture in this learning unit on buffers and then our second lecture in this learning unit on titrations together here as we sort of consider this weak acid, strong base titration. And why it's kind of emerging is we are still talking about titrations, but one of the things to think about is if we start with just a weak acid, we don't have a buffer in that situation. But as we start adding in strong base and converting some of that weak acid into its conjugate base, well, then we start making a buffer in solution. Because remember, a buffer consists of a weak acid and its conjugate base. So that's why we can sort of think of it as merging some of these two subjects together. And so some of the calculations that we're going to see in today's lecture sort of have a mix of stuff we did with buffers in our first lecture and then with titrations in our second lecture. So again, conceptually, we're going to continue this concept of doing calculations that we refer to as being dynamic, meaning we're constantly changing things. And that's what happens when we're doing titrations. We're still going to consider the same points that we could be in a titration, either before the titration has begun, before the equivalence point, at the equivalence point, or after the equivalence point. So since we already went through those concepts in our second lecture on just dealing with titrations with strong acids and strong bases, I'm not going to go through that process in terms of how do we determine where we are in reference to an equivalence point, but again, we'll just build on the calculations from that. So again, skills that we see here are still finding pH during a titration. Because we're going to be dealing with weak-strong combinations, we have a few more homework problems that will allow us to practice that. So again, today in lecture, we're going to do the weak acid, strong base, and then kind of setting up for our in-class activities and problems that we'll work through, which will be a weak base with a strong acid. So again, reminding us of kind of our cheat sheet that we have here. So this is what the titration curve is going to look like. And again, what's unique with this one compared to our last titration with the strong-strong combination is having this buffer region. So remember, when we start here and we just have a pure weak acid, we only have a teeny tiny bit of that conjugate base. But as we start titrating in strong base, it's going to convert some of that weak acid into its conjugate base. That's kind of how that buffer works, right? We're going to sacrifice the weak acid army as we react it with this strong base, and it's going to make some of our weak base army. So as we decrease the concentration of our weak acid and begin increasing the concentration of our conjugate base, we begin to have a buffer solution. So remember, when we have a buffer solution, that means we're able to use the Henderson-Hasselbalch equation. So that's when we start seeing Henderson-Hasselbalch here as a mechanism for determining pH. I will show you that you still can use ice tables, but in this situation, if you know you have a buffer, the easiest way to calculate pH is just using the Henderson-Hasselbalch equation. But you'll notice that we only have one spot. It is going to be this spot after we've started and before the equivalence point that we can use the Henderson-Hasselbalch equation. If it's before we've started or after, or I'm sorry, at the equivalence point, we do still need to use an ice table. So that's why ice tables will always work. They take a little bit more work to kind of go through and solve them. You can start sort of taking shortcuts, and you guys will begin to start recognizing the spots where you can take shortcuts. But again, I want to just make sure to highlight that there are some spots here. If you don't have a buffer, you cannot use the Henderson-Hasselbalch equation. So we'll review, we'll refer back to this kind of cheat sheet at the very end after we've done all of these calculations here. So I'm not going to take a lot of time and go through sort of the qualitative analysis of this titration curve, only because we've sort of highlighted the different spots in our titration. I will just kind of point them out here and remind us of where we're at and what's there and so forth, but I'm not going to take as many minutes here on these introductory slides because we dealt with these when we first did titrations in our last lecture. So before the titration begins here, again, we've not added any hydroxide, so the only thing that we have here is our weak acid. And for this example problem that we're going to do, it's going to be an acid that we call propionic acid, which we just abbreviate HPR. So this guy will be the conjugate base when we take off our H+. So you can see that's what we have here in solution before we've started, just that weak acid. Now there may be just a teeny tiny bit of PR minus, but insignificant in terms of an overall contribution to anything with regards to pH. So when we begin our titration, and again, it's going to be anywhere along this spot after we've started and before the equivalence point, we are in this region that we call before the equivalence point, and in this titration, this will be a buffer region. So we're going to look specifically here at 20 milliliters into the titration. So what's happening is we are neutralizing some of that or all of that hydroxide that's being added by our weak acid that's there. So what's going to happen is some of this weak acid is going to react with the hydroxide and get converted into water and its conjugate base. Again, we're going to have sodium spectator ions there, but not anything we're concerned about. But the important piece is once we have a mixture of weak acid and its conjugate base, we have a buffer. So that means we can use the Henderson-Hasselbalch equation to calculate pH, but we can also always use an ice table. So what we're going to see in terms of the pH is because there's a change in sort of the ratio of the army that we have there, we do see a slight increase in pH, but not the same amount that we'd see if there wasn't anything in solution and we were just adding straight sodium hydroxide to water. Okay, just a little comment here. Even though HA is a weak acid, when we bring this strong base in, it's enough to rip that proton right off. So even though this is going to be holding onto its protons more strongly than our strong acid. Let me say that again because that can get confusing. When you have a strong acid like we had with our last problem, like hydrochloric acid, strong acids hold onto their protons weakly. They let go of them because they live as H+ and then the conjugate base. So even though this weak acid holds onto its proton more strongly, once we add in a strong base like hydroxide, it's going to automatically just rip the proton off. And so that chemistry is going to be one way. And we'll see that when we do our ICF table. Okay, so that's kind of an important point to highlight there. When we are at the equivalence point, this is where things again become a little bit different from what we saw with our strong-strong combination. At the equivalence point, and again in our example problem, we're keeping the concentrations and the volumes pretty simple, so it's easy to see when we're at the equivalence point. We are going to have 40 milliliters of our weak acid, so when we've added 40 milliliters of our strong base, that's the same concentration, we will be at the equivalence point. So all of the hydroxide has used up all of our weak acid. So if we think about what we have in solution at that point, we're going to have the sodium spectator ions that are left over. All of our weak acid has been stripped of our protons, so the only thing that's left is the conjugate base. And all of the hydroxide has taken those protons from that weak acid and converted them into water. So what's unique about this situation is because it contains the conjugate base of a weak acid, the pH will be greater than 7. So again, a weak base solution will be slightly basic. And we can see this at our equivalence point here. We can see that the pH is not equal to 7, which is what we saw with a strong-strong combination. The pH is going to be greater than 7. A way just to simply remember this, if you were to see a qualitative question, when you have a weak-strong combination here, the strong indicates where the pH will be at the equivalence point. Because the base is the strong component, the equivalence point will be more basic than pH 7. So the last thing to move on to then is what do we look like after the equivalence point? Well, at this point, we're still going to be adding in hydroxide. So we've added 20 milliliters past our equivalence point. So all that's going to be happening then is we're just adding hydroxide straight up to the solution. There's no weak acid there to help neutralize it. So we're just going to continue to accumulate hydroxide in solution. And when we change the hydroxide concentration, we are increasing the pH. So that's why we see what we have there. So in truth, our titration curve and our titration calculations after the equivalence point for a strong and a weak strong combination are going to look very similar. Okay, so here what we're going to do, and hopefully because you've got a little bit of a familiarity with working through the calculations for titrations with our strong, I'm going to sort of set up the problem a little bit for you, and then I'm going to tell you what the answer is here, and then I'm going to encourage you to pause the video and try to work through and see if you can get to the answer. If you aren't certain how to start or getting stumped a little bit, again, I will reveal the answer sort of in stages so that you can continue to pause and maybe work through. Or if you're feeling really uncomfortable, you can just let the video play and see the worked out solution. So 4 points to this weak strong titration. First point is before the titration begins. So just to highlight what our titration is, we've got 40 milliliters of 0.1000 molar propanoic acid in our beaker. And then we've got 0.1000 molar sodium hydroxide in our burette. So by these concentrations being the same, it's super easy to see where our equivalence point is going to be. It's when we've added the same volume of sodium hydroxide. So it's going to be 40 milliliters of sodium hydroxide. But obviously before the titration begins, the only thing that we have in solution is 0.1 molar propanoic acid. And so this becomes like a chapter 18 problem. So like in chapter 18, if I asked what's the pH of a 0.1 molar propanoic acid solution, given this Ka value, you should be able to tell me what that pH is. So go ahead and try and see if you can get a pH of 2.94. If you're struggling, again, let the video play and you'll see a worked out solution. So kind of working through this first problem, and I didn't reveal this one in stages since this is kind of a review from chapter 18. If we think about what's there, we have HPR in solution and it's 0.1 molar. And again, the volume is sort of insignificant to determining the pH because whether we had 40 milliliters or 400 milliliters, the concentration is going to be the same. No chemistry to consider at this point because we really haven't added any sodium hydroxide, so there's also no volume change to consider. So all we have is a weak acid that's going to dissociate into its conjugate base and some H+. So we set up our ice table like we normally would. We've got 0.1 molar HPR. We make the assumption that we have no H+ or PR- from any other sources. So this is again how it's a little bit different from what we did in our first lecture. When we had a buffer, we had a value that we put here. This is not a buffer solution right now. It's just a solution of a weak acid. So there's 0.1 molar there. So some of this is going to dissociate and make some of the conjugate base and our H+. We complete our ice table with our equilibrium values and put those into our equilibrium expression to solve for X. I've promised you that I will not give you a problem where you have to do anything other than make an assumption to solve for X. Making an assumption that X is small, again, allows us to simplify and easily solve for X here. X is equal to 1.14 times 10 to the minus third. Because that is also equal to our H+ concentration, we can take the negative log of that, and that will give us our pH of 2.94. So hopefully that was pretty straightforward for you guys, a review from the kinds of problems you're likely to see in chapter 18. And again, this is the kind of problem that you might see on the fundamentals quizzes, which are on equilibria. So moving on to the next piece, we are looking at before the equivalence point. And again, for your test, you're probably not likely to be given this piece of information letting you know that it's before the equivalence point. But again, here, if you know that there's 30 milliliters that have been added, and we know the concentrations of these two are the same, we can tell that we haven't yet added enough sodium hydroxide to neutralize all of the propanoic acid that we have, so we must be before the equivalence point. So the answer that you should get in terms of what's the pH of this solution is 5.36. So I encourage you to pause the video, see if you can begin working through this problem to get that answer. This is a part of the problem I will reveal in stages, so if you're getting a little bit stuck, feel free to press play, let it go on to the next stage. Once you get a little bit more of a setup and some hints, pause it again and see if you can work through to the final solution. So always the first thing you want to do is ask the question, who's there and what chemistry might be going on? So at this point in the titration, again, we've got our propanoic acid. It's 0.1 molar, and we had 40 milliliters in our flask. Because we know we're going to be doing chemistry after we've begun our titration, we do need to convert into the number of moles of each species that we have. So we've got 0.004 moles of HPR. And again, sodium hydroxide, we don't really need to consider the sodium here. We know that's going to be a spectator. But with the hydroxide, if we've added 30 milliliters of 0.1 molar sodium hydroxide, we know we've added 0.003 moles of hydroxide. The chemistry is always going to be the same for a weak acid, strong base titration. We are going to be taking a proton off of our weak acid by our strong base, generating water, and then the conjugate base of that weak acid. So knowing that we've written a chemistry equation, not an equilibrium equation, that tells us that we need to have an ICF table here. So if you want, go ahead and pause the video, see if you can finish out the ICF table, knowing the values that we have here. So working through our ICF table here, again, even though we knew that we were before the equivalence point, knowing that we have less hydroxide than we have weak base, that is again going to be our limiting reagent. It's going to be completely used up, and we'll see that we still have a little bit of our weak acid in solution at this point in the titration, again, before the equivalence point. Finishing out our ICF table tells me how many moles of each species I have remaining. I've got 0.001 moles of my HPR. My limiting reagent, which was the hydroxide, is completely gone. And importantly, and this is a very important piece, I do generate some of the conjugate base. This is important because the conjugate base is a species that can generate a contribution to pH. So remember, ICF tables are going to give me the number of moles of each species that I have. If I want to get to concentration, I have to take the number of moles and divide by the volume that they're contained in. And that's why volume changes are really important when we consider titrations. You have to add together the volume that you started with and the volume that you added from your burette to get the total volume that these moles are contained in. So again, to get the new concentration of each of these, we will take the number of moles that we have and divide by 70 milliliters, obviously converted to liters to be able to get molarity. So go ahead and try to get those values, and then once you figure out what your concentrations are of these two, try to use that information to now solve for pH. As a hint, you can either use an ICE table, or since we know we've got a weak acid and its conjugate base, you could use the Henderson-Hasselbalch equation. So first, let's go ahead and calculate what those concentrations are. Again, dividing by the total volume that we have, we get new concentrations of our weak acid and our conjugate base. Now again, I gave you a hint that you could use these either in an ICE table, or because we know we have a weak acid and its conjugate base, we could use the Henderson-Hasselbalch equation. So first, let's look at an ICE table. So again, this ICE table is going to look similar to the ICE tables that we did at the beginning of this chapter when we were talking about buffer solutions. So we just calculated what these concentrations are. And again, that's what we just got over here. It's very important that we are no longer going to be using the 0.1 in here. That's not what we have anymore. We've done some chemistry. Some of that has been used up. So these are the new concentrations of weak acid and its conjugate base. Now remember, whether we put a minus x or a plus x right here, we're going to make an assumption. So that x will go away. So don't worry about what that is. Again, completing our ICE table to get our equilibrium concentrations with our variables, we can go ahead and use our Ka value in order to determine what X is. And remember, X is going to give us the hydronium ion concentration. So feel free, pause this video here again if you want to try working through that on your own, or let it play to see the worked out solution. Solving for our X, remember we're going to use our Ka value. We're going to be putting in our equilibrium expressions, using an assumption to allow small values of X to be eliminated from our algebra here. Notice that we don't eliminate these values or this X, right? So again, this is a problem just like we had at the beginning lecture from this chapter. So once you solve for what your x value is, and I apologize, I don't have it there, take the negative log of that value, and that will give you the answer of 5.36. Notice that if you use the Henderson-Hasselbalch equation, knowing that you had a buffer, again, taking negative log of the Ka value and putting the concentrations of the conjugate base and weak acid in their corresponding spots, you'll see you can get the same answer of 5.36. All right, moving on now to at the equivalence point. One of the things to highlight here, you'll notice the answer to this is not 7 like we had with the strong-strong combination. The pH for this is 8.79. So if you want, pause the video here, think about what you have in solution at the equivalence point, and see if you can use that information to get a pH of 8.79. Again, if you want, let the video play, see if you can get a better understanding just walking through the worked out solution. So again, at the equivalence point, and I'm treating each of these problems as though we started kind of from scratch, even though this is kind of a solution that's been dripped in all along. From a calculation standpoint, you're only going to get one of these problems on a test, so you can kind of treat it as though you've added all of this 40 milliliters at once. So again, 40 milliliters of our weak acid gives us 0.004 moles of our weak acid. Adding the same amount of the same concentration of our strong base gives us the same number of moles of hydroxide. Remember, even though we have the same number of moles of sodium cation, not contributing to anything with pH because it's a spectator ion. You'll notice we have the same chemistry equation here as we had when we were before the equivalence point. That's not going to change. But what changes is the fact that we've got equal amounts of each of our species that are reacting, our weak acid and our strong base. This is what we call stoichiometric equivalence. We've got equal amounts of both of our reagents. So in reality, both of them are limiting because we end up with none of them at the end. So the concentration of HPR that's left after the dust has settled from this titration is 0 molar. The concentration of hydroxide is 0 molar when we consider the end of this titration. Now, keep in mind, this doesn't mean that the pH is going to be equal to 7. Remember, I told you in the last slide it's not equal to 7. And this is the reason why it's not equal to 7. When the dust has settled, what we have left here is a conjugate base of a weak acid in solution, and not an insignificant amount of it. We've got 0.004 moles of it. So again, if we know that that's contained in 80 milliliters because of the two solutions we mixed together, we know that the concentration of this weak base, this conjugate base of a weak acid, is 0.05 molar. So what we have to do is ask the question, well, how would that contribute to a change in pH? And again, I want to highlight here, we cannot use the Henderson-Hasselbalch equation to solve this problem because we don't have a weak acid and its conjugate base. We only have the conjugate base at this point. So if you'd like, I'm going to give you a hint here. Try pausing the video, seeing if you can work this out. If this is the only species we have in solution with water, show me an equilibrium equation for what goes on with that, and then how you could solve that to figure out the pH. So here's the worked out solution. The equation needs to change because if this is the only species we have in solution and then water is the only other thing that's available, what is going to happen is this conjugate base of a weak acid is going to grab a proton from water, generate our weak acid, and leave behind hydroxide. So why this is significant is we are generating hydroxide in solution. Okay, so a couple of things that make this problem sort of unique. This is not unlike, imagine you were to have, say, sodium propanoate, NaPr, the salt of the sky. That's kind of like a chapter 18 problem. And if that salt were put in solution and this were all that you had, this would be the equilibrium that you would write. So this is where this becomes really important. This is a base equilibrium. So if we're going to do any ice tables and any solving for X, we need to use a KB value because that's the kind of chemistry that we wrote. Now, they gave us a Ka value, but we know we've got an important mechanism for interconverting Kb and Ka values using Kw. So some really important things here for this at the equivalence point. The chemistry is that of a weak base, the conjugate base of a weak acid. So we have to write a base equilibrium expression and use a Kb value, which in this case we actually have to calculate. Once we have those pieces in play, the ICE table and solving for X are just like we've always done. Okay, now the only thing that's in solution is 0.05 molar of this propanoate, this conjugate base of propanoic acid. So these guys are both zeros. So we know our equilibrium is going to shift with these values or these signs of X's. But again, it's not going to matter because we're making an assumption. So we've got two X's on top, 0.5 minus X or 0.05 minus X on the bottom. Our assumptions in solving for X using again this Kb expression get us to a value of hydroxide concentration as 6.2 times 10 to the minus 6 molar. Now be very careful. If you take the negative log of just this number, it's going to give you POH. POH is 5.21. Make sure you've got your logic hat on and you say, wait a minute, if I've got a weak acid, strong base titration, the equivalence point pH should be greater than 7. So that should be a reminder that that's not right in terms of a pH. But again, seeing that my X was equal to hydroxide concentration, negative log of that is POH. So to convert that to pH, I can do 14 minus that. Remember, you could have gone around the block the other way and converted hydroxide concentration to H3O plus and then taken the negative log of that to get to pH. Those will both work. Remember those around the block calculations that we did in our last chapter. We get to the answer of 8.79, a pH greater than 7 for a weak acid, strong base titration. Now keep in mind, some of the questions that you might see on your exam are quantitative, where I might ask you to calculate the pH at this point, or it might be a qualitative question, and I might just ask you, at this point in the titration, will the pH be less than, equal to, or greater than 7? And in that point, you'd need to sort of use your logic hat and say, I know for a weak acid, strong base titration, the pH at the equivalence point will be greater than 7. All right, last calculation for today's class, dealing with what's the pH after the equivalence point. So again, always do your kind of thought process of what's there, what chemistry is happening, what changes are there in volume, do I need to think about any equilibria? The answer for this is going to be 12.04. So go ahead, see if you can run through these calculations, see if you get an answer of 12.04. Again, if you want to just let it play, go ahead. I don't think I have too many stages revealed for this problem, but again, this has a lot of similarity to what we saw in the after the equivalence point titration with our strong titration from last class. All right, so again, thinking about what we have in solution, going through this titration from the starting point to the finish, again, 0.004 moles of our weak acid, 0.005 moles of our strong base. So if we set up our ICF table to kind of see what the dust settles on after our chemistry is done, the chemistry equation here you'll notice has been the same all throughout. So we've got 0.004 moles of HPR, and now we've got an excess of our hydroxide. So our HPR is now our limiting reagent, so that's gone. And we're going to have 0.001 moles of excess hydroxide at the end. I'm going to address this in just a minute here. We do have some conjugate base produced, 0.004 moles of PR minus that's produced. So I'll address that in just a second here. So again, we've got none of our weak acid left. If we've got this excess of hydroxide, to figure out what the new concentration is of hydroxide, we can take that number of moles, divide by the new volume that we have to get this concentration of our hydroxide. Negative log of that will give us POH. 14 minus that will give us the pH. Now, what I'm going to talk about here is nothing that you need to do at all when you do a calculation, but I just want to convince you why in this problem it's okay to ignore the fact that we make some conjugate base here. So again, hopefully everybody's good recognizing we're going to have none of our weak acid left, but we are going to have some conjugate base left. Okay, we're going to have the 0.004 moles of it that was generated. Once we divide that in the 90 milliliters it's contained in, we're going to have a weak base concentration of 0.044 molar. So the question is, do I need to think about that in terms of its ability to contribute to pH? Remember, when we are at the equivalence point, it was important to consider its contribution to pH. Okay, so let's flip to just to the next page. I want to make sure to highlight this is not anything you have to do. It's not necessary. I just want to prove to you why you don't need to worry about this. So again, let's imagine thinking about after the dust has settled, we've got some PR minus that's in solution, and we're going to ask how much that can do this type of an equilibrium chemistry and contribute to OH minus. One of the things I want to make sure to point out though, don't forget, we still have some OH minus that's in solution after that dust has settled. That's that 0.011 molar that we use to calculate pOH. So the fact that we've already sort of filled up this bucket over here means we're going to slide even less over to this way. But let's still go through the calculation and see how this works out. So again, let's imagine that we are going to slide a little bit of it over and make a little bit more hydroxide. And let's solve for X like we did with our at equilibrium calculation. Knowing we have to have a Kb expression, we need to use a Kb value. We can put these values in from our equilibrium, assuming that X is going to be small, and solve for X. And we can see what X is going to be. That X, 3.1 times 10 to the minus 9th, is so insignificant compared to 1.1 times 10 to the minus 2 that it's basically enough that we can ignore it. So we really don't need to worry about that. So I just wanted to make sure to show you, or as proof of principle, highlight why we can ignore the contribution of this guy to any more increase in pH. We wouldn't have to worry about that. Okay, we really only need to think about worrying about the hydroxide that we generate, or that's in excess, as a contribution to pH. Okay, so I'm going to flip back and forth here just for a second to just summarize and remind everybody what we did. So before the titration began, we had our weak acid that was just sitting in a little beaker below our burette. In that case, if we wanted to figure out what the pH of that was, we needed to use an ice table, just like we did if we had a weak acid solution from chapter 18, our last learning unit. So we needed to use the Ka value for that weak acid, an ice table, solve for X, and then once we knew the concentration or the amount of acid that dissociated, the negative log of that would give us pH. So again, I'm just going to take a second and go back to that slide and just remind everybody what that calculation was. So that calculation was right here, right? We had a weak base in solution. We had to do an ice table, just like we did in chapter 18, using the equilibrium constant for this weak acid. Our X that we're going to solve for is H plus concentration. Negative log of that gives us pH. So pretty straightforward. That one is basically just sort of reviewing what we had from chapter 18. Before the equivalence point, again, we always are going to be using an ICF table when we're doing chemistry. We need to figure out the chemistry that's happening, and after that dust settles, who's left, and figure out the concentrations of species we have left. Since we know any point here that we have before the equivalence point, we're actually taking some of our weak acid and making it into a conjugate base. Having both of these guys in solution, we know we've got a buffer. So we can use an ice table, but we can also use the Henderson-Hasselbalch equation. So going back to that calculation here, that is going to be here, right? Here was sort of our chemistry table to kind of show us who we had left, and again, the concentration of conjugate base and weak acid that we had. And we can go ahead and solve that either using an ice table, or because we know we have a buffer, we can use the Henderson-Hasselbalch equation. So you'll notice this is the only time that we can use a Henderson-Hasselbalch equation in this titration is when we are in this buffer region, which occurs before the equivalence point. At the equivalence point, again with a weak acid strong base combination, we know that the pH is going to be greater than 7. So after we sort of do our ICF table to sort of figure out what are the concentrations of things, then we can use our ICE table, and then we need to do a KB because we are looking at base chemistry. So let me go back to that one and just make sure that everybody's good with that piece. So again, here's the chemistry that we had. The chemistry was stoichiometric equivalence of our weak acid and the strong base that we've added. So the only thing left in solution after the dust settles is our conjugate base of that weak acid. But that conjugate base of that weak acid has base potential. It has the ability to grab a proton from water and leave behind hydroxide. Because we did base chemistry, we have to have a base equilibrium and we have to have a KB value that we use. That KB value is going to allow us to solve for our X, but that X is hydroxide concentration. So a lot of unique things that we need to do in order to get to the correct pH, which is going to be 8.79. So the last little piece to kind of highlight here is, all right, what if we're after the equivalence point? And one of the things I want to highlight is that we have the same directions here for after the equivalence point for a strong-strong combination or a weak-strong combination. We still want to be using an ICF table to kind of see after the dust settles with that chemistry how many moles of who we have in solution. What we're going to see though is it's really going to be the hydroxide that we have in excess that's going to be contributing to pH. An ICF table will tell us the moles of hydroxide we have in excess, so we need to divide by the total volume we have in that point of the titration to get us concentration. That concentration again will be hydroxide, so taking the negative log of that will give us POH, 14 minus will give us POH. So just flipping back for a second to that final slide that we had here for that, right? Oops, it's going to be this slide right here. Here's our ICF table to show you after the dust settles, who do we have? Yes, we've got excess hydroxide. We do have some conjugate base of our weak acid, but again, I hope I convinced you that this is not something we need to worry about after the equivalence point to contributing to pH. The major contribution is going to be from the excess hydroxide. The number of moles of excess hydroxide divided by the new total volume that we have is going to give us hydroxide concentration. Negative log of that gives you POH. Subtract that from 14 to give you pH. And just as a little way to highlight here, this is why we don't do a weak-strong combination as well, because it starts to get muddy with what you sort of have at certain points because you kind of have competing things going on. All right. So one of the things, if you'd like to try to work on this problem on your own, I'm not going to post a solution here because I would like it to be something that we work on in class. So whether or not you want to wait and work on it in class or want to take a stab at working through it here and then you could ask questions, we're going to have a problem here for a strong acid, weak base calculation here. So I'm going to post that when I post this video. I will actually post just kind of what the directions are for that titration. Okay, so kind of look for those instructions if you want to work on that on your own, or again, I will make it available in class for you to work on during class, in our class next lecture, face-to-face sort of lecture period. So kind of summarizing, again, we've been doing titrations here, and so we've been doing acid-base titrations where in this lecture we were doing a weak-strong combination. So again, the picture here is reminding us from our previous lecture when we did our strong combination. We are now doing a weak-strong combination. So again, still the same 4 points that you're going to be asked one of on a test. So again, you won't know what combination it's going to be, strong, strong, weak, strong, strong, weak. and you won't know which sort of point in the titration. So you got to know how to do all of them, both qualitatively, being able to predict what the pH is likely to be, less than 7, greater than 7, at 7, but also do the calculations. All right, so that wraps up kind of our flipped video here for you to watch on weak acid, strong base titrations.